All right, we want to be able to differentiate composition functions, not just simple functions that we've seen so far. So suppose that we're given the function h of x is equal to 3x squared, well, the square root of 3x squared plus 2x plus 1. So we're asked here to find functions y and u such that y compose u of x is equal to h. So we want two functions such that when we plug one into the other, we're going to get this h of x, this radical. So our goal is to come up with a y of u and a u of x. Now y of u is going to be the outside function, and u of x is going to be the inside function. That's how we can think of this. So y of u is going to be the square root of u, and u of x is going to be 3x squared plus 2x plus 1. So if we were to write this as a composition, y compose u of x, that's equal to y of u of x, which is y of 3x squared plus 2x plus 1. Remember that y of anything in this case is the square root of anything. So for us, y of 3x squared plus 2x plus 1 is the square root of 3x squared plus 2x plus 1, which is h. So this is decomposition. We're taking some large function and we're breaking it down into smaller functions. So let's say that we have an r of x, sine of the square root of x minus 1. We have a y of u, which is going to be sine of u, and then we have u of x, which is the square root of x minus 1. But notice that this thing isn't decomposed enough, because we can still break down u of x here. So we have to figure out a way such that when we write this thing out, it's going to be in terms of all basic functions. So let's look at u of x. We're going to break this down now so that we have y1 of v, which is the square root of v, and then u1 of x is the x minus 1. So if we compose those two functions, that's how we end up with u. So the chain rule is going to allow us to take the derivative of these types of functions. So before, where we might be able to just differentiate y equals the square root of x, now we can differentiate y equals the square root of x squared plus 1. Before we could do cosine x, now we might be able to do cosine of 2x. Y equals x to the 9, now we could do something like this polynomial to the 9th. Or sine of x, now we could do sine of, well, raised to the 4th of 3x squared minus 5. So here's the chain rule statement. Suppose that g is differentiable at x and f is differentiable at g. The composition, big F, is equal to f composed g, defined by f of g of x, has derivative big F prime. And that's going to be given by this thing. F prime, big F prime, is equal to f prime of g of x times g prime of x. Now if we were going to break that down like we did just a minute ago into y equals f of u and u equals g of x, then we're going to have this thing right here. dy dx, the derivative, is given by dy du times du dx. And this can be a really simple way to look at things. It can also be really complicated. So find the derivative of y equals the square root of x plus 1. So we're going to use that second one stated there. And so we have to break it down to y of u and u of x. So remember that y of u is going to be the outside function. U of x is the inside. So the derivative of y with respect to u, 1 over 2 square root of u. Derivative of u with respect to x is 2x. And so all we have to do is multiply them, and that's our derivative. And we're going to replace that u there with what u is really equal to. So there's our derivative, and we can simplify a bit. Find the derivative of sine of 2x. So again, y of u is the outside. Its derivative, sine of u, the derivative is going to be cosine of u. U of x is the inside. 2x, the derivative is 2. And so when we multiply those, we get dy dx. So dy dx is dy du times du dx. Now this one is where it gets complicated. So I'm going to allow you to read through this because we have a double decomposition here, and that means that we're going to have a few different things to multiply to get to our derivative. So you can see here's the normal breakdown, y of u1 and u1 of x, but then we also have y of u2 and u2 of x. So we have to find both of those derivatives, du2 dx and dy du2. And that's how we're going to end up here with 6x cosine of 3x squared minus 5. And we also have to do it for the first one. So that's how we would end up with the full derivative, because du1 dx is the same as du2 dx, the thing we just found there. But I don't think it's good to look at it this way. I think the best way is to look at that top statement. F prime, big F prime, is equal to f prime of g of x times g prime of x. That basically means that we want to take the derivative of the outside times the derivative of the inside, and we would just keep going with that. So let's actually take a look at doing it that way. Find the derivative of the same function. Now, we have the derivative d dx of sine to the 4 of 3x squared minus 5. So that's really the same thing as sine of 3x squared minus 5, that whole sine function raised to the 4th. So f prime is going to be, well, we have to take down that 4, sine cubed of 3x squared minus 5, times the derivative of whatever it was that was raised to that 4th power, which was sine. So times the derivative of that sine function. Now we know that's going to be cosine of 3x squared minus 5. So here's our derivative. But we still have that inside function, so we're going to do times the derivative of the inside again. So times the derivative of 3x squared minus 5, which is 6x. And we just simplify. Now, had there been another inside function, we would just keep multiplying by the derivative of the inside over and over again.